We are diving straight into Depth Anything 3, or DA3. The full title is Recovering the Visual Space from Any Views.
And this one is a really big step forward. It takes the Depth Anything series way beyond just single image depth.
Right. It's about full, consistent geometry from any view.
That's the core mission. The model aims to predict a spatially consistent 3D structure from basically any visual input you can throw at it.
So a single image, a whole collection of images, even the video stream.
Exactly. And here's the critical part. It works whether you know the camera poses ahead of time or not.
And I think the most exciting part really is how they did it.
Mm-hmm.
They call it their minimal modeling strategy. And for anyone just tuning in for the key insight, this is it. DA3 basically argues that we don't need these super complex, specialized architectures for 3D anymore.
That's the whole argument. They show that you only need two sort of minimal ingredients. First, the architecture. It's shockingly plain.
Just a transformer.
Just a single vanilla pre-trained vision transformer, a dyno encoder, basically. No heavy custom architecture needed.
And the second ingredient.
A singular, really elegant prediction target, the depth ray representation. This one change completely sidesteps the need for complex multitask learning.
And that elegant simplicity, it just crushes the benchmarks.
Oh, completely. DA3 sets a new state-of-the-art on their new visual geometry benchmark, and the margins are not small.
I saw the numbers. It surpasses the prior SOTA, which was VGDT, by an average of, 35.7% in camera pose accuracy?
And 23.6% in geometric accuracy. It is a clean break from the old way of doing things.
Okay, let's unpack that minimalism, because it sounds almost too good to be true. I mean, traditional methods like structure from motion or multi-view stereo, they were these hyper-specialized pipelines.
Right, each one solving just one tiny slice of the problem.
So how does DA3 unify all of that with just a, quote, minimal model?
It's a complete reframing of the problem. They just treat geometric reconstruction as a straightforward, dense prediction task.
Pixels in, pixels out.
That's it. You give it n input images, the model spits out n corresponding depth maps and n-ray maps. Simple as that.
The novel depth ray representation seems to be the star of the show here. Why predict this ray map instead of just going straight for the camera parameters, the rotation and translation?
It solves a fundamental mathematical headache.
Okay.
When you try to predict an explicit rotation matrix, you slam right into the constraint problem of what's called the special orthogonal group, SO3.
Orthogonality constraint. Your matrix has to be perfect.
It has to be perfect, and that is notoriously difficult for a neural network to learn with standard loss functions. The tiniest error just ruins the geometry.
So what does the ray representation give us instead?
Simplicity and robustness. The ray map, they call it R, is just a six-dimensional vector, R6.
Oh, like R6.
It contains the ray origin, that's T, and its direction, D, for every single pixel. This vector implicitly captures all the camera's pose info without those rigid constraints.
And turning that into a 3D point?
It becomes trivially simple. The 3D point P is just the origin T plus the depth times the direction D. You avoid all that instability.
That is a genius simplification. But wait, you still need the explicit camera parameters, right? The rotation R and the intrinsics K for a lot of downstream tasks.
You do.
Does DA3 just lose that capability then?
Not at all. And that's the clever part. You get the stability during training, but then at inference time, you can just extract the explicit camera parameters from the predicted ray map.
Oh.
Using well-established geometry methods, the direct linear transform algorithm, DLT, and then RQ decomposition.
Ah, so DLT and RQ decomposition. For anyone not familiar, that's basically a classic matrix trick to sort of peel apart the camera's internal settings from its position in space.
Precisely. You're trading complexity for just, a bit of stable math at the end.
Got it. Okay, so architecturally, as you said, it's just a standard Dyno V2 transformer. But how does a standard model handle the AnyView part? I mean, an arbitrary number of cameras.
This is where it gets really interesting. The cross-view reasoning. They do it with an input adaptive cross-view self-attention mechanism.
So no complex 3D feature fusion or anything like that?
No. It just dynamically rearranges tokens in some of the later layers, the ones they call the LG layers.
And that dynamic rearrangement is the key.
It's crucial. It lets the model share information across, potentially hundreds of views without the computation just exploding. They found a sweet spot. A ratio of 2 standard layers to 1 cross-view layer.
Get your local features first, then bring in the global context.
That's accurate.
And the output layer, the dual DPT head. What's the thinking there?
It's designed to make sure the two outputs, depth and ray, are tightly coupled. It processes the same features through shared modules, but then uses distinct fusion layers, which forces the model to learn the interaction between the geometry and the pose.
So the model has this elegant architecture. But elegant models are useless without mountains of clean data.
Mm.
And this is where DA3 runs into, well, a problem as big as 3D vision itself.
Yeah.
Messy, real-world data.
That's the challenge they faced. To train a true generalist model, you need massive, diverse data sets.
But real-world data, stuff from CoLNAP or WildRGBD, it's often noisy, sparse, incomplete. It's a mess.
Totally. You can't learn high-fidelity geometry if your training labels are just full of holes and artifacts.
So how do they get around that? This is where the training story gets really interesting.
They used a very robust teacher-student distillation paradigm.
So a teacher model.
Right. And this teacher is a dedicated monocular depth predictor. Crucially, it's trained only on a massive corpus of synthetic data.
Things like HyperSim, Obgiverse.
Tartanair, yeah. The V3 datasets, they call them. And because this data is synthetic, it's perfect. The teacher learns incredibly fine geometric detail without any of that real-world noise.
I noticed they made some key improvements to this teacher over, say, depth. Anything too. First, it outputs depth, not disparity.
Right, which is better for real-world distances. It's also scale, shift, invariant.
And second, it uses an exponential depth representation. Why is that important?
Exponential depth, it really helps enhance the model's sensitivity in the near-camera regions, which are critical.
Right, where things can get blurry or merged together.
Exactly. Linear depth estimation often struggles there. Exponential depth sort of stretches out the representation in that close-up space, giving you more fidelity.
They also added a new loss function that I found fascinating, a distance-weighted surface normal loss. What does that do?
It's a key refinement for preserving local geometry. Basically, when you calculate the normal for a surface, you downweigh the influence of neighboring points that are farther away.
Ah, so the resulting normal is much closer to the true local surface.
Much closer. It makes a huge difference for the crispness of edges and surface details.
Okay, now for the most important part, the distillation step. Teaching DA3 with this super smart teacher.
So the teacher generates this high-quality relative pseudo-depth for the noisy real-world data. But, and this is key, they don't just use it raw.
They align it.
They align it to the noisy metric ground truth using a robust RANSAC scale shift procedure.
And that RANSAC alignment is like a protective measure.
It is. It lets them keep all that sharp geometric detail from the teacher while still correcting the label's metric scale and completeness. They're basically fixing the holes in the real-world data using the perfect synthetic knowledge. The visual difference is night and day.
So for the final DA3 training, they actually transition. They start with a noisy ground truth, but after 120,000 steps, they switch entirely to the teacher's aligned pseudo-labels.
Which just shows you how valuable that synthetic foundation is. It confirms that clean synthetic data can teach generalizable geometry better than messy real-world data can.
Provided you have a good way to anchor it back to real-world scale.
Exactly. The RANSAC alignment.
Okay, so DA3 wasn't just measured against old benchmarks. The authors actually established a whole new comprehensive visual geometry benchmark. Why did they need a new one?
Because the old benchmarks were too narrow. They'd focus only on monocular depth or only on pose estimation.
But to test a generalist 3D foundation model?
You need something that covers everything, and this new benchmark does. It covers pose, geometry, and rendering across 5 really diverse data sets. HiRoom, ETH3D, DTU, 7 scenes, ScanNet++, Cope.
That's a huge range, from controlled object scenes to massive indoor environments.
It really is.
So let's talk numbers. How do they measure performance? For pose.
For pose, they use the area under the curve, or AUC. It's derived from relative rotation and translation accuracy. They look at it at thresholds of 3 and 30 degrees or centimeters. A high AUC3 score means you have really strong alignment.
And for the actual 3D reconstruction quality?
For that, they take the predicted poses in depth, and they fuse them into a 3D structure using TSDF.
Truncated sign distance function. A classic volumetric representation.
Right. Then they measure the accuracy of that volume with the F1 score, and for dense point clouds like DTU, the chamfer distance.
And looking at the results tables, the big DA3 giant model is it's completely dominant.
It's not even close. You're seeing gains of up to 33% relative improvement on key pose metrics, like the OS3 score on ScanNet++A over the previous state-of-the-art. That kind of margin is huge.
And it's not just pose, right? The reconstruction accuracy is also top tier.
It sets the new standard. DA3 Giant outperforms VGGT and Pi 3 by an average of 25.1% relative improvement in post-resettings. It just proves that this depth array idea is robust enough to rebuild the world from scratch.
Here's the point that should get every engineer excited. The smaller DA3 large model, which is only 0.36 billion parameters, it actually outperforms the 1.19 billion parameter VGGT in half of the settings.
That's an incredible efficiency gain. It's not just an academic win. The speed is also unprecedented. The tiny DA3 small model runs at over 160 frames per second. It's actually deployable.
The ablation studies are the final nail in the coffin for the complex models, aren't they?
Yeah.
They tested the minimal depth plus array setup against other options.
They did. Things like depth plus point cloud plus camera, or just depth plus camera.
And the minimal setup won.
Across the board. The depth plus ray configuration had nearly a 100% relative gain in that tough OSSI 3 pose metric compared to just using depth and camera parameters. It confirms that the six-dimensional ray vector is doing the heavy lifting.
Okay, let's switch to applications. How does having this superior geometry model actually advance other 3D tasks? Let's talk about novel view synthesis with 3D Gaussian splatting.
Right, so they applied DA3 to feed-forward novel view synthesis, or FNVS. And again, they stuck to the minimal philosophy. They didn't build some new complex NVS model. They just fine-tuned DA3 by adding a simple head, a GSDPT head, to predict the 3D Gaussian parameters for every pixel: opacity, rotation, scale, color.
And the really surprising result here is that these simple fine-tuned geometry backbones like DA3, they substantially outperform highly specialized purpose-built NVS models like Pixel Splat or Depth Splat.
That is a critical insight for the whole field. It confirms that the path to better photorealistic rendering might not be through more complex rendering models,
but through better, more generalized geometry foundation models.
Exactly. Superior geometric understanding directly translates to massive improvements in FFNVS.
And for real-world use, they even made a pose-adaptive version.
Right, which is designed to be robust out in the wild. It predicts the Gaussian splatting parameters in the local camera space, and it uses the DA3 backbone to handle the inputs, whether you give it camera poses or it has to predict them itself.
It really feels like we're seeing generalist foundation models start to dominate these tasks that used to be reserved for highly specialized networks.
I think so. That core ability to just understand geometry has been unlocked in a unified and really efficient way.
DA3 has definitely made a powerful statement. It proves we don't need these convoluted multitask architectures. A plain pre-trained transformer and the right minimalist target, the depth array representation. That seems to be the path forward.
The authors themselves see DA3 as a foundational step toward truly versatile 3D foundation models. They suggest the next steps are extending this to dynamic scenes, integrating things like language and interaction, and of course exploring even larger scale pre-training.
So here's the final thought for you to mull over. We've seen how dramatically this foundational approach to geometry improved a complex task like novel view synthesis. So what other critical 3D vision areas, think about next autonomous driving, surgical robotics, or even sophisticated mixed reality, what's going to be fundamentally redefined once it's built on top of DA3 level spatial understanding?